Variation of conductivity and molar conductivity with concentration. How does the conductivity vary with dilution or decrease in concentration? Conductivity and molar conductivity change with the concentration of the electrolyte. Conductivity decreases with decrease in concentration for both weak and strong electrolytes. So, why does the conductivity decrease upon dilution or decrease in concentration? It is because the number of ions per unit volume decreases upon dilution. So, conductivity decreases with decrease in concentration because the number of ions per unit volume decreases upon dilution. How does the molar conductivity vary with dilution? Molar conductivity increases with decrease in concentration. What is the reason? It is because the total volume of the solution containing 1 mole of the electrolyte also increases. We know that lambda m is equal to kappa into V. So, upon dilution, as volume V increases, molar conductivity increases. How can you define molar conductivity? Molar conductivity is defined as the conductance of the electrolytic solution kept between electrodes of a conductivity cell at a unit distance, but having area of cross section large enough to accommodate sufficient volume of the solution that contains 1 mole of the electrolyte. Now, when concentration approaches 0, the molar conductivity is known as limiting molar conductivity lambda naught m. How does the molar conductivity change for a strong electrolyte like potassium chloride and for a weak electrolyte like acetic acid? For a strong electrolyte like potassium chloride, the variation of molar conductivity with concentration is given by the equation lambda m is equal to lambda naught m minus A into C raised to half. This equation is of the form y is equal to mx plus C. So, if a graph is plotted taking lambda m along the y-axis and concentration raised to half along the x-axis, a straight line graph will be obtained with slope equal to minus a and intercept equal to lambda naught m. What is lambda naught m? It is the molar conductivity at infinite dilution or zero concentration. So, for a strong electrolyte from the graph, it is clear that there is only a slow rise in the molar conductivity upon dilution. Why there is only a slow rise in molar conductivity in the case of strong electrolytes? This is because a strong electrolyte is completely dissociated. So, upon dilution, there is no much change in the degree of dissociation alpha. But we know that lambda m is equal to kappa into V. Since volume increases upon dilution, molar conductivity will also increase. Consider a weak electrolyte like acetic acid. From the graph, it is clear that there is a steep rise in the molar conductivity upon dilution in the case of a weak electrolyte. What is the reason? For a weak electrolyte, we know that the degree of dissociation alpha is low at higher concentrations. But upon dilution, alpha, the degree of dissociation increases. Since alpha increases, the total number of ions will also increase. Therefore, molar conductivity increases steeply upon dilution for weak electrolytes. In the case of potassium chloride, how can we obtain lambda naught m, that is molar conductivity at infinite dilution? By extrapolation method. Extend the line for potassium chloride so that it will meet the y-axis at a point. Lambda m value at that point gives lambda naught m. But for a weak electrolyte, lambda naught m cannot be obtained by extrapolation of lambda m to 0 concentration. Therefore, lambda naught m for a weak electrolyte is obtained by using Kohlrausch's law of independent migration of ions. Kohlrausch's law of independent migration of ions, the law states that the limiting molar conductivity of an electrolyte, that is lambda naught m, can be represented as the sum of the individual contributions of the anion and cation of the electrolyte. Thus, we can write lambda naught m is equal to V plus lambda naught plus V minus lambda naught minus. Lambda naught m is the limiting molar conductivity of an electrolyte. V plus and V minus are the number of cations and anions. Lambda naught plus is the limiting molar conductivity of the cation. Lambda naught minus is the limiting molar conductivity of the anion. Applications of Coleridge's law. Using Coleridge's law of independent migration of ions, it is possible to calculate lambda naught m for any electrolyte from the lambda naught of individual ions. For example, consider sodium chloride. Lambda naught m of sodium chloride will be equal to lambda naught m of sodium ion plus lambda naught m of chloride ion. Then for weak electrolytes like acetic acid, it is possible to determine the value of dissociation constant. The dissociation constant is Ka. Once we know the lambda naught m and lambda m at a given concentration C. The degree of dissociation alpha is given as equal to lambda m by lambda naught m. Once alpha, the degree of dissociation, is calculated, we can use it to calculate the dissociation constant Ka, and Ka is given as equal to C alpha squared by 1 minus alpha.